Koto. Kia ora, welcome to my talk. Thank you very much for inviting me. It's a great privilege, and I'd just like to say how much I've enjoyed these when they started over lockdown. And yeah, it's been a really nice tradition, so I'm really pleased to be talking. So yeah, I'm going to talk to you a little about some of the mostly modelling work that me and my colleagues have been doing over the last many years. I've been modelling and interested in coastal dune systems since I moved to Otago in about 2002. So I might sort of, I won't guess what beach this is, but it's actually Summerlands Beach on Phillip Island. So it's actually an Australian beach with my colleague Teresa. So I'll come back to what we were doing on that beach a bit later on, but this is quite rare. This is a modeler in the field, and I'm just down here underneath my name, so it doesn't happen very often. Okay, so I'm going to be talking about dunes, and we probably all know this, but I think it's a really timely reminder as to why we need dunes and what are the threats. So I've just put a whole collection of pictures up here, so of some of the things that are local and of interest to me and of interest to Dunedin, which is where I'm based on the east coast of the South Island, almost at the bottom. I think it's about the most southern university you can get in the world. So the two pictures on the left are of St Clair seawall and some damage that happened a few years ago. So there was a big sinkhole happened, we can see it here, and this seawall is constantly being damaged by the waves and big storms. But we also know that we get lots of damage to properties that are very close to the coast. And one of the ways in which that can be sort of mitigated, or we can help protect people who live on the coast, is very expensive geoengineering. We have some examples of that in Dunedin with our seawall. We have some sort of sand sausages as well, but they tend to be very expensive, and often they only last for a certain amount of time. And with increasing storms, greater inundation threat, we need to maybe do something that's a bit more adaptive. So our dunes are very important in this work. Just to come into Dunedin a little bit, because it's the place I know probably best, along with Stewart Island. So this is just an example from our council website as to some of the things that are happening on our coast. And this is really just that stretch of beach in St Clair. So we can see here the geotextile tubes that are put to protect the old landfill that are behind these, that is sort of dates from sort of around the 1800s and contains who knows what, old building materials, so it could be quite nasty. And we can see that actually it costs us as ratepayers a real load of money, even as quite a small place. And there's lots of different ways in which the council are exploring or have used in the past to protect the dunes. So some of the work I'll be talking about today from my PhD student is based around here, the John Wilson Drive end of this sort of our town beach in Dunedin. The other thing I just want to point out before I get to the science is this is from our local paper, the ODT, and we can see from, and this is as far back as the online stories go, 2010, all the way up to a few days ago, we are getting stories about our beach, and this our one particular beach, St Clair, St Kilda. We have groups that are pushing for particular solutions. We've now got a council and a coastal manager who is actually doing lots of extensive consultations. So our dunes are really important to us, and our beaches are really important to us, and we need to make sure that we have long-term solutions that don't keep costing us money. So our dunes come in many shapes and sizes, and they have lots of, from a modelling point of view, lots of really complex things going on. They tend to be really large. This is a shot of the parabolic dunes on Mason Bay, Stewart Island. We obviously have moving sand, and this is one of our notches, or it could be, you know, for example, it's like a blowout. We have vegetation cover, so this is marron grass, non-indigenous species in New Zealand, and we have different vegetations that cover our dunes in different places. We obviously have, when we look at the wind, variable wind speeds, variable wind directions, and when we tend not to have vegetated dunes, we'll have very dynamic morphology. So our wind and our waves, particularly in our storms, will move our dunes and change the shape of them. So I think all of these are really challenging things when we want to come to model and understand a bit more of our dunes. So what are some of the big questions that myself and along with my colleague Mike Hilton from the geography department and our sort of various PhD students over the years, but particularly our current PhD student who's just handed in his thesis, are interested in. So particular, what's the interaction between the form, the morphology, the wind flow, the sediment transport and the vegetation? Can we sort of help, oops, sorry, I'm a bit too handy on my mouse there. Can we build conceptual models or help extend conceptual models for dune development that are applicable across these dynamic landscapes? So can we use the predictive power of modeling to help us with that? And can we use the knowledge to develop mitigation plans to help protect our coastline? And I've just sort of put up sort of from Bernie Bauer, his 2012 sort of conceptual model of how the wind is moving transport over a beach dune system. So we use accommodation. Like I say, I don't really do the field data, although I will talk about how actually useful it is for me to go out into the field sometimes. So as a group, we see the value of using both field data and computational flow dynamics modeling. We see that they have complementary sets of data and they can help us understand the situation in many different ways. I think the thing to note is that they're both expensive, they're both time consuming, they both have limitations. We get often really good time data from our field studies. We tend to get better space data sets from our modeling efforts. So yeah, I'll sort of leave it at that. We can come back to that in questions. But we can see we do a variety of different things. We look at sediment transportation, we model, not model, we actually measure the wind, and we have to sometimes do things like vegetation surveys to understand what is on our dunes. So these are some of the methods that we've used and we'll be talking about today. So in our field work, use of 2 and 3D anemometers, wind anemometers, sand traps, sand traps, both passive and active, so pot traps, and these are active designed by Mike and myself, are active sand traps that move with the wind, so we're always pointing in the direction of the wind. And yes, we did make those out of plumbing pipes, so they're very much, yeah, sort of cheap, but very effective. We also have sand counters, which are laser counters, and we do things like vegetation surveys. In our CFD modelling, when I started doing these extensively almost 20 years ago, very much two-dimensional modelling, just because of our computing capacity. We now do sort of large, relatively large scale three-dimensional modelling. So we can sort of model, not quite at a landscape scale, but certainly at a sort of part of a dune scale, and you'll see some examples from my PhD students' work. We also model real and ideal topography. So real coming from, for example, LiDAR data. So we have a real dune surface, and ideal where we try and capture some of the features of the dunes that we think are important for the flow. Okay, so I'm going to sort of, for the rest of the talk about a series of papers, really, hopefully to sort of tell you a story. And the first three are based around work that Mike and I have done with our PhD student Duke at St Kilda Beach, which is in Dunedin. So we can see we have our dune here, our foredune. We have John Wilson Drive above it, and beyond that are golf courses and housing, often slightly below sea level. So the dune and John Wilson Drive play a really important role in protecting South Dunedin from inundation, etc. And we can see a sort of shot along John Wilson Drive here, so we can see the dunes. And Tom Simon-Smith is the coastal manager at the DCC, and his masters, I think it was 2016, they cut 3 notches in the foredune as a first attempt to try and move some of the sand from the beach over the foredune or through the foredune to the swale. So the swale is the place between the foredune and John Wilson, the very steep slope of John Wilson Drive, in attempt to sort of see whether it worked, see what some of the parameters were, but also is this a way of actually getting the sand to move through the beach and create a little bit more dynamicism in the morphology to help sort of maybe protect what's going on and behind the dune. So this first paper published last year looked at, and it was a combination of field and CFD work, looked at how incident wind angle and topography affected flow through the notches. So after these initial 3 notches, a whole series of, I think it was about 20 notches were cut at various different angles and sort of sizes, lengths in this section of foredune. So it was a really extensive investment by our council to do that. And they've, been very invested in the research that we've been doing here. So the field work, we looked at what the flow's doing sort of across the notch, sort of around the middle of the notch on one particular notch C. And you'll hear notch C being talked about a lot, to see what happens to the flow. So this is some of the data. We had a sort of good, and that's always the downside of field data. You never know what weather you're going to get, but they did actually get some good data gathered. Wind direction, so pretty consistent, reasonably consistent periods of wind direction, but some different wind directions as well that varied from almost shore normal to almost along shore, which was really useful. And we can see a whole variety of wind speeds. Now we're interested in sediment transportation ultimately, so we're usually interested in wind speeds above around 10 meters a second, roughly. And this was from our incident, our sort of mast that measured instant wind. Duke, and I won't go through this is in the paper, so if you want to know more about this, there's quite extensive appendices about how the sensitivity analysis was done, but Duke went through a very extensive and thorough sensitivity analysis for his modelling of the notch to make sure that we had as best validation as possible. We validated against various sort of parts of this field data. Okay, so I'll come on to the results because that's really sort of the most interesting thing. So we're interested in approach, sort of incident wind angle, and what happens in the notch at various wind angles. And we can see that we had, so I have to get this right, most western is virtually a longshore wind. Most southern we can see, and these are the arrows on the side, is virtually shore normal. So our beach is sort of down here at the bottom of the pictures. And not surprisingly, what we saw in this was from the field data, there was a decrease in wind speed when the wind angle increased. So what do we mean by that? As we went from shore normal or more shore normal to alongshore, as we go down these images, we see that our arrows within the notch here are getting much smaller. And A2 was our second anemometer on the mast, so at almost ½ a metre from the surface, and A4 was the top anemometer on the mast at about 2.5 metres. And we can sort of see that, for example, alongshore, we're getting around the same sort of wind speed magnitude, but we're getting very different direction. And so depending on whether, obviously our lower anemometer was much more in the notch, whereas the one at 2.55 was sort of hovering around where the foredune top was, crest was. So yeah, for A2, our lower anemometer, the wind in the notch shifted from notch parallel to more easterly as the wind became more westerly. So we can sort of see that. So we can see for more shore normal, we're getting roughly the same angle, but it changes direction sort of reasonably significantly as we get more longshore winds. For A4, so that's our top anemometer on our mast, the wind in the notch is approximately parallel for almost all our wind directions. So then looking at a line through from the beach through the notch, so along the sort of centre line of the notch, so beach is on the left, all the way through to the deposition load, or just about the deposition load of the notch, and we can see that here. We can look and examine, so the top graph is a non-dimensional velocity, and we can see it sort of splits into two sort of types of behaviour. So the top three are our more onshore winds, so the red is the most onshore, and then it's gradually becoming more alongshore, and our bottom two are much more alongshore, and we can see that there's this difference in behaviour. The next graph down, that is our direction, sort of horizontal direction and wind angle direction, and our bottom is our sort of up and down vertical wind direction. And so we can see again differences with our incident wind direction. And so, and the other thing we can note from this is that we have these three zones of different flow behaviour. So beach, upper beach to notch throat, and then the notch itself, which is not surprising. You know, we're changing morphology, we're funneling our flow into a sort of relatively narrow notch. We're going to get increases in speed, we're going to get changes in direction. We just want to know how that occurs with the different wind directions and wind speeds that we get on this beach. And can we sort of more generalize it? Is that helpful? So looking at, this is a non-dimensional velocity plotted. This is from our CFD. Again, a sort of along a centre line from the beach through the notch. From onshore to alongshore, we can see really how our flow is changing. And very much, we're getting very little of our flow, not surprisingly, for an alongshore wind. And looking at a plain sort of contour plot through that, we see from onshore, we're seeing sort of through the notch that we're getting a sort of speed up, sort of increase in velocity event, but then by the time we get alongshore, we're getting very low velocities through the notch. And this led us to a sort of conceptual model, I suppose. So how is incident wind speed and incident wind angle, how is this related? And this is within this one notch, although obviously more work needs to be done to look at other notch morphologies. So what we saw with this notch is that we had an approach steering threshold angle of about 27 degrees relative to the notch long axis. So and what that meant was sort of up to 27 degrees of the notch angle from the incident wind, we had notch activation, where we got flow compression and acceleration of the flow through the notch. After that threshold angle, we got flow separation and deceleration. So we got a different flow behavior. But what we saw was that it depended on the incident wind speed. So that was only the case when our flow was definitely above 8 meters a second, but actually that threshold of incident wind speed actually increased depending on what the incident wind angle is. So remember, down here on the left, that's shore normal. And way over here on the right, that's alongshore. So we needed much, much higher wind speeds to get any sort of notch activation for those alongshore angles. So this was a really nice sort of conceptual model to start thinking about how wind was flowing through the notch. So this is the second paper we published from Dept's PhD work, and this was really then looking at the sand transportation through the excavated notches. So this was really concentrating on measuring or trying to measure what was going on in terms of that sand transportation. And so this was using, this data was using the Wenglers, which are the laser counters. They're actually designed, I think, to count pills, drug, tablets. But they're relatively a little bit sensitive, but sort of seem to be pretty good at counting grains of sand going through them. And again, what we saw, we got a variety of conditions across the experiment. This was just a spate of a sort of few minutes, really. But we got some changes in wind angle, where our longshore angle was 77 degrees. We got a variety of wind speeds. But what was interesting was we saw that only certain combinations of those wind speeds and wind angles gave us sediment transportation. Sorry. Sometimes reasonably high, we're getting up here counts of sort of 1,000 odd. So, so we can sort of see when the notch was inactive in terms of transportation going through it and when sand transportation occurred. And this was our setup, and this is just some pictures just showing some examples during this field work where we see some sort of freshly deposited sand on the east of our notch. And remember, our wind is coming sort of this way from the east to west. So it's coming along here and into the notch. And Duke also, he just did simulations of the wind. We didn't include the sediment in there, so just a one-phase simulation, but it did give us a really good indication of what the flow was doing through the notch. So we can see this is looking from the beach into the notch. We can sort of see as it comes in at a reasonably alongshore angle. We can see how the flow is steered through the notch and why we might be getting our deposition on this side around mast B, because our flow slows and we're getting sort of the sand dropping out of its transportation. And we can see when we look at the wind profiles, the vertical wind profiles of our sort of virtual masts here, we can see that our mast B, remember, this is where we're getting the sand deposition, has a different sort of profile than mast D. So again, this is a really good example of sort of the complement of our field data with our CFD. We're not using one or the other, we're using them together to sort of understand the situation and using them in complementary ways. So again, this led Duke to develop this conceptual model, which is this one was all about how these notches are creating this conduit for sand transport to the back of the dunes. So where our notch orientation is really important with respect to our incident wind angle, and that effective notches for moving the sand sort of behind the dune definitely depends on prevailing wind conditions. So if you're going to use this type of intervention to move the sand, create, you know, for whatever reason, whether they're ecological or just sort of mitigation against climate change effects, then you really need to look at site-specific information. So where are your prevailing winds coming from? What are you trying to do? But they certainly, this work can certainly help those coastal managers with their excavation parameters. Okay, so we're going to look behind the dune now. So, and this was purely CFD modelling work. And this was because we wanted to do something. We wanted to use that predictive power of modelling. We were pretty confident that our models, you know, with the validation that we'd done, were, you know, were okay. They're never going to give you exact numbers or values, but we felt that we could use them in this predictive way to help us understand what happened if we change our dune morphology. You know, now that's a very expensive thing to do in the field and do in real life, but actually if we can do a bit of modeling that helps us understand what's going on, then, you know, that's great. So what do we have here? Well, first of all, we wanted to look at what was going on in the swale. So we have the beach here, we have the dune, and then this is our John Wilson Drive with our, it's really, as you can see, really high. It's obviously a solid structure, it's immovable. What's going on in the flow here in the swale? And we can see it depends on our incident wind angle, whether we get recirculation in that swale or not. And so Dirk, first of all, did a whole series of simulations looking at different incident wind angles, incident wind angles, and seeing what happens. We see that when we get up to sort of shore normal, we're getting quite complex flow happening in the swale here, and we're getting these vortices and really complex things. And in real life, our swale is very vegetated, and we're not accounting for that except through a roughness on the surface. So we know that this isn't, you know, completely real life, but it is giving us an indication of some things that are happening. And just some shots here from our modelling. So looking down, it's a little difficult to tell, but here are our notches. This was a model where we looked at more than one notch. We actually looked at multiple notches together. So it was a much bigger simulation, geometry-wise. But interesting, then concentrating on the swale and looking to see what happened. And we can see as we get more shore normal, the one at the bottom, we're getting this more helical flow in the swale, not surprisingly. But when we've got a long shore, that the pattern is very different. So we're getting flow acceleration for an incident wind that's above about 74 degrees for this situation, and flow reversal in the swale in that situation as well. The pictures on the right are from some pot traps that were set during storms for over a 4-year period, just showing where sand deposition occurs. So it's a little difficult to say, but the letters indicate where the notches are. And so we can see red is deposition. We can see high deposition sort of behind, in the swale behind our notches, which is what we expected and what we see. So that's good. So looking at the effects of the backdune morphology, so this is where we manipulated our geometry in the model to look and see what two things do. So the first one we're looking at is what happens if John Wilson Drive is moved back, if the distance between the lee of the dune, the back of the notch, and John Wilson Drive changes. So we see here the current situation where, sorry, John Wilson Drive is very close relatively to the back of the notch or the back of the dune. So the swell is quite narrow. And then we see a situation here in B where it's been moved back by, I think that's 50 meters landward. I don't think the golf course would like that very much, but you know, we'll see what happens. It might be better for Dunedin if that happens. And then in C, it shows us what happens if we alter the slope of John Wilson Drive. We saw that John Wilson Drive has a slope, I think, of about 30 degrees. What happens if we change it from 0 to 90? What happens to the flow? So on the right, we see what happens, first of all, if we actually change the width between John Wilson Drive, the width of the swale. And we see in the bottom that actually what happens to the recirculation in the swale changes. And we get to a point where we get recirculation in all of that swale. And eventually, as the distance increases, the recirculation is sort of limited more to the lee of the dune. So that's sort of an interesting result that can really help us. And we can see what happens to the velocity. This is the elevation, so we can sort of see our swale distance here is increasing, and this is what's happening along the centre line of the notch, sort of through to the swale of what's happening to the velocity. So we're seeing that we're sort of moving back and we're getting some interesting things happening in this increasing width of swale. These two images, or the graphs and the images now, are showing what happens if we change the slope of John Wilson Drive. So we're keeping the swell width constant, and we're changing from a very extreme, I mean, it would never get to this, but you could imagine it might be the result of, you know, sort of very extreme storm damage, or, you know, something like that. So, you know, maybe it is more realistic. And we're seeing here a cut through showing what happens to the recirculation. This is, I think D is our normal slope, and we see as we go from 0 that that vortex, or that recirculation behind the dune, between the dune and John Wilson Drive, really changes, and it can get quite complex. So Doug then did a whole series. He covered all of the dune slopes and widths and came up with this conceptual model, which I think is fantastic. So we're looking at 4 locations here: beach, in the notch, at the notch lobe, and in the swale. And we're looking at the slope and the width, and these are the combined effects of these on the normalized wind speed at about ½ meter from the bed. And so what we're seeing is that at the beach, it doesn't make that much difference, as you would expect. We've got no influence of the dune really there, or John Wilson Drive. So we're just getting, you know, virtually the same velocity. This is all for 1 wind speed. For in the notch, we can see this sort of, you know, relatively linear sort of relationship between the width and the slope. And the same at the lobe, a little bit more pronounced. But in the swales, what's quite interesting, we've got this sort of band here where the relationship is different from the others. So these can then be combined into this more sort of model where we've got these 3 zones. And these are all about where the recirculation happens, whether it happens in the whole swale, on the lee of the notch, because all of these have implications for our sand transportation and, you know, how effective the notches and the swale and the protection are. So this one's about to be submitted. So we haven't actually published this yet, so it's still being worked on a little bit. Okay, I'm going to switch focus now for the next sort of last sort of 5 minutes or so. Hopefully that's okay. Just to talk about some work I've been doing with particular interest for me on what's happening on the surface of the dune. So as we know, a lot of coastal dunes are vegetated or partly vegetated. And in modelling, we've traditionally sort of ignored this. If we do anything, we tend to just put a term in the Wall law model to model that roughness. So, you know, a constant value, but often it might just be a sort of sand roughness equivalent value, and we don't really take into account what the vegetation is, what it's doing. Now, if anyone's ever been on the beach, we know that the vegetation A, this is marram grass here, we can see how tall it is. It can often get to 0.5 metre in height. And when the wind blows, it bends over. Now, this was actually where the benefit of being out in the field was really useful for me, because I actually sort of suddenly thought, well, actually, there's a different roughness going on here. As the wind blows harder, surely the roughness is changing, and the effect of the vegetation actually means that it's a smoother surface. So we got a little bit of funding from the university, and so we decided to have a look at this and try and see if we could come up with a dynamic roughness model that we could implement into our CFD code. So we did some field experiments on Summerlands Beach, on Phillip Island, and Mason Bay in New Zealand. We looked at 3 different vegetation plants and 2 sort of dune shapes or sizes. So the first lot that we did, and this is a picture of our experimental setup at Summerlands, was a very low dune. It's about 1 metre high. It's very sparse vegetation. We had sort of 3 patches, some seaweed grass and spinifex and mixed with seaweed grass. Whereas on Mason Bay, we had a very high foredune, 10 to 15 metres. We had very dense, tall vegetation up to 0.5 metre. That was all marram grass covering the Stoss slope and the crest. We put up towers with anemometers on them, 4 anemometers. We hoped for good weather, i.e. lots of wind and lots of different wind velocities. And we got a whole series of nice bits of data that looked like this. And from there, we sort of chopped out some relatively constant wind direction, wind speed segments. Those were plotted, sort of log of the height versus the wind speed, put a linear regression line through it, and the intercept is a roughness value. We did those for as many different wind speeds as we could to come up with a sort of, hopefully, a more dynamic understanding. Oh, that's just a... And these are our, now I have to say, we had to work with the data we got, and we were a little bit limited in our wind speeds and wind directions. But what we particularly found, I'll concentrate on the Mason Bay marram grass data here on the right. We actually had a mast on the beach, which I can talk about. That's sort of something interesting going on there. We had a mast on the Stoss slope, which was covered in marram grass. And this was the benefit of being out there for the experiments. I hadn't realised, but actually that vegetation was growing in the prevalent wind direction. So actually we had a different sort of relationship between roughness and wind speed than I actually thought we would have. And then we had marram grass on the crest, which was much more upright. And we had a sort of what I thought was a more typical model. So I'll start with a more typical model. On the crest, what we saw was, that at lower wind velocities, as we increased our velocity, our roughness increased roughly. We reached a peak and then it decreased. So our roughness got rougher up to a certain threshold velocity. And the reason for this, we think, is it was behaving like wheat in a field. It was sort of waving around, and that was actually increasing the roughness. It then got to this threshold where then it really just laid over, and then our roughness became smoother the stronger the wind blew. On our Stoss slope, because our marram grass was already lying flat, what we found was that we just got smoother. As the wind velocity increased, our roughness became smoother. What we found on the beach, although it was a very subtle effect, we found that actually as our wind velocity increased, our roughness on the beach actually became rougher. And the reason for that, we're speculating, is that all the nice fine sand that was smoother got blown away. So you're just left with sort of rougher sand. So what have we done with this? Well, this was my lockdown project, and this belays the pain it was coding this into Fluent. This took me months because it was actually very difficult sort of connecting this model up to a bit of commercial software. But we now have a model, a bit of code where we can actually change the roughness depending on what the velocity is 5 meters above the dune surface. And I did a couple of quick simulations, and what we can see is, not surprisingly, on the stoss, that makes very little difference. On the crest of a dune with this dynamic vegetation model, there's some small differences, particularly to the speed up we get at the top of a dune, but in the lee it does make quite a big difference to the recirculation and the flow recirculation. This is still to be published, and we're still working on the simulations, but I think it's a really interesting, relatively straightforward way to at least account for some of that dynamicism in the vegetation roughness. This is just an example of some of our flow. And then I'm just going to quickly talk about sort of something that was a little bit more novel to me, which was using machine learning to see if it could tell us and help us with understanding what was going on over a dune. And the idea here was that sometimes with modelling, we want to assess many different parameters. We had 5 in this experiment, and we wanted to put lots of different values to those parameters and see which was the most important. In this case, for predicting recirculation or turbulent structures at the stoss toe and also in the lee of the dune. And I won't go into the machine learning because that's not really my thing. I did this with a colleague at Waikato. But what we found was that we could use a relatively simple target or value and that the machine learning did a pretty good job of predicting whether we were going to get turbulent structures or not, i.e. whether we were going to get vortices or not. And that actually was really helpful. As we see here, with all the parameters, we could have done up to, I think it was 400 odd simulations. We didn't want to do that, lots of computer time, no time to actually go through and assess all of the results. This gave us a really good way of sort of able to be then cherry picking which were the interesting cases, and actually come up for this particular experiment and these particular dune forms, what was having the most effect on those turbulent structures being there. So for example, wind orientation angle turned out to be our number one, not surprisingly, but some of these other things like dune height, dune slope, crest width, we saw whether they made a difference or not. So you'll have to read the paper. I haven't got time to explain more than that, but I thought that was a really interesting use of sort of machine learning and CFD in this sort of environmental modeling sort of space. So always got lots more to do, lots more field work. We've got lots more planned on our notches. Luckily, it looks like Duke might be staying with us to do a postdoc on something else, but we'll have a bit of time to help us do some more dune stuff. And we've got more of the CFD stuff that we hope is going to get published or is in review at the moment. So I've given you a really, really quick overview of some of the stuff we do. So I'm sorry if I've gone very quickly, but yeah, if anyone's interested, of course, they can always come and talk to me. And I just thought I'd finish on this. So thank you to all my collaborators, and particularly Duke, he couldn't be here today because he's out doing field work with Mike. Yeah, thank you for him for allowing me to talk about his work. This is the reason why I don't do field work most of the time. I wasn't here, this is my colleagues. But also this is a picture, I just put this in at the last minute, from my PhD actually. I did a PhD looking at the formation of dunes. So, you know, I've come sort of full circle in the last, I won't tell you how many years, quite a few years. So yeah, thank you very much. Sorry if I gabbled and I've gone too long, as I always do.